Hi class, Professor Dave here, and we are basically in week 4 on probability. This presentation will cover the following 7 items: basic probability, complementary events, compound events including mutually exclusive, the addition rule, conditional probability just lightly, independence just lightly, and we'll introduce and work with the multiplication rule. So the big motivating idea for probability is that it has major applications in life, business, marriage, driving, personal life, etc. Uncertainty is pervasive, and not dealing with it doesn't make it go away. If you can deal with it, you will have an edge in life. So certain business practices don't make any sense without it, like financial hedging, insurance, or safety stock inventory. And probability theory provides the tools for dealing with uncertainty. All statistical inferences are probabilistic, and thus are the whole field of probability is essential in statistics, and that's why we study in statistics. But it has a ton of merit in its own place, and I use probability all the time. I get into my car and drive knowing that the probability is pretty low. I drive carefully because I know probability. And I get into airplanes knowing that the probability of being injured is low. Okay. So there's 3 methods for computing probability. One is subjective probabilities, and that is just your best guess from all your previous experience. Another one is relative frequency approximation. You just run an experiment. If you wanted to know what the probability of a double was when rolling a pair of dice, you could just do it many times and see how many doubles you get, divided by the total number of times that you did it. That'd be an approximation to the probability. The other approach is sometimes called the classical approach, but it's really direct calculation, and that's what we'll be concentrating on, is calculating probabilities. So to formalize the second method, relative approximation, relative frequency approximation, probability of event E is just the number of times the event E occurs divided by the total number of times that you tried the experiment. Again, calculating the probability of a double, you roll it 200 times, you get about, 12 doubles, and then you have it. Okay, so here's an example. For a recent year, there were about 6 million car crashes amongst 134 million cars registered in the United States. So what's a probability that a particular car gets into a crash? Well, you just have that number over the total number. This is like running an experiment. So how many car crashes out of the total number of cars? So maybe about 5% of cars get into a car crash. Okay. The classical approach, or the direct calculation, is the same thing. Probability of an event is the number of ways the event can happen, which is S divided by the total number of equally likely outcomes, or simple events. Now, some definitions: an event is any collection of results or outcomes from a procedure. A simple event is any outcomes or events that cannot be broken down any further. And a sample space is a set of all possible simple events. The sample space is key for calculating probabilities, so we'll look at that. You flip a coin, what's a sample space? Well, the sample space, flipping a coin once, is just heads and tails. You roll a die, the sample space is just 1, 2, 3, 4, 5, and 6. These are simple events, they can't be broken down any further, and you can, and they're equally likely. What about flipping 2 coins? Well, the real sample space is heads, 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 tails, tails, heads, and tails, tails. Not that you get 0 heads, 1 head, 2 head, or 3 heads. That's not it. Well, 2 heads, 1 head, or no heads. But if you got 1 head, that head could be broken down into whether it was a head or a tail and a head, so that's not a simple event. But a simple event would be head, tail. That can't be broken down any further. So that's our sample space. And flipping 3 coins, those basically, each coin could be either head or tail, or 2 events for each coin. So 2 times 2 times 2 is 8. So there's 8 events. And basically all of these, which is 2 coins, and then the first coin, or the first coin could have been either heads or tails. So you can put heads in front of all these or tails in front of all those. And you can get your sample space like this, and there's 8 events. Heads, 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 tails, tails, heads, tails, heads, tails, tails, and now put a tails in front of them all. So there's your sample space. Okay, so some simple probabilities. What's the probability of exactly one head and 2 flips of a coin? Well, the sample space was that. Exactly one head. There's this way or this way, so there's 2 ways it can happen out of 4. So probability is 2 over 4 or 0.5. What's the probability of exactly 2 heads and 3 flips? Well, our sample space is this. And there's exactly 3 ways you can get 2 heads. And so it's 3 out of a total of 8. And so it's 0.375. What's the probability of getting at least 1 head and 3 flips of the coin? At least one head, there's at least one head here, 2, 3, 4, all of them except for tails, tails, tails. So that probability is 7 divided by 8, or 0.875. All right. Now, unusual to be picked. Say we had a class of 27 students and we randomly select one to win a prize. Would it be unusual for you to win if you were in this class, where unusual is a probability less than 0.05? Well, how do we calculate it? Probability of you winning is 1 out of 27, which is actually 0.037. So that is less than 0.05, so in this classification that would be unusual. Most likely you would not win, and the not winning would be the complement of that. Okay, so now all probabilities are between 0 and 1, because either it can't happen or it has to happen. Okay, and here's a little graph of that. Impossible is 0, certain is 1, pretty likely is up here, 50-50 chance, unlikely down here. Okay, so what's the probability of getting a double when you roll a pair of dice? What do we need? We need a sample space. So let's have a sample space. The first roll has 6 possible outcomes, the second roll has 6 possible outcomes, and any combination is fair. So we can multiply those together, and there should be 36, 6 times 6, or 36 elements in the sample space, and here it is. Of course, you can get a 1 on the first roll, 1 on the second, 1, 2, 1, 3, all the way to 1, 6, and then all the way to 6, 6. So there's 36 elements here. Each one's equally likely, and it can't be broken down any further. Now the sum could be 6, but that could happen in a number of ways. But 3, 3 is clearly a simplement that cannot be broken down any further. So here's our sample space. So what's the probability of a double? Well, how many doubles do we have? We have the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6 out of 36. So the probability of a double is just 6 out of 36, or 1 6, or 0.167. So there's some basic probability calculations, and of course feel free to move the video back to catch anything that you missed. It's a nice thing about videos. Okay, so complementary events, either the event occurs or it doesn't. So the probability of the event occurring plus the probability of it not occurring must be equal to 1. Either you come to class or you don't. Either you have blonde hair or you don't. Either you wear glasses or you don't. Stuff like that. So a little bit of algebra. If we move this over here, we have the probability of an event is just 1 minus the probability of it not happening. Or the probability of it not happening is 1 minus the probability of it happening. And the complementary rule, which this is, will be used. You'll use it. It's very intuitive. You'll use it without even thinking. Okay, so some examples, right? Roll a dice, find the probability of not getting a double. Well, probability of a double was 1 6, so the probability of not getting a double is 5 6. Flip a coin 3 times, find the probability of getting at least 1 head. Well, what's a complement of at least 1 head? Go ahead and think about that. Stop the video. Well, the complement of at least 1 head the other way is no heads. So 1 minus no heads. How do you get no heads with all tails? It's just 1 out of 8 of those events, or 7 out of 8. Then 1 minus 1 over 8 is 7 out of 8. And so we can get that probability by the complement rule. Okay, if the probability of passing this class is 80%, then what's the probability of not passing? Well, just the complement, 20%. Okay, so some examples there. Now it goes up the more that you understand and the more that you study, so feel free to watch this video many times. Okay, so number 3, probability of a combination of events. If A and B are 2 events, then nomenclature, the probability of A or B is the probability that A occurs or B occurs or both. That's inclusive or, and it's like the union of A and B. The probability of A and B means that A and B both occur, and it's the intersection of A and B. So to get used to that, we take a look at a couple of things. Say we roll a die and consider the following events. Event A is the observation is 4 or more. So A is 4, 5, and 6. And event B is the number is even. So B is 2, 4, 6. So find the probability of A or B and the probability of A and B. Well, what is A or B? A or B is, well, A or B means it's an A or B or both. So we have to combine these. Combining these, we get all of A and also this 2 and B. So 2, 4, 5, and 6. So the probability of A or B would just be 4 events out of the total 6, or 6 rolls, a roll of a dice. You can either have 1, 2, 3, 4, 5, 6. So out of 6 possible outcomes, or 0.67. Now what's the probability of A and B? What's in both A and both B? Well, just 4 and 6. So 4 and 6. What's the probability of A and B? That'd be 2 elements out of 6 for a roll of a die, and that's 1/3 or 0.333. These just happen to be complementaries. They don't have to be. They happen to add up to 1 right now, but it doesn't have to. Okay. So mutually exclusive, you can see the mutually exclusive or disjoint means that the events cannot occur at the same time. So mutually exclusive or disjoint looks like this. In general, we have overlap, and that would be not mutually exclusive. And you can kind of see the A and B here. If that's A and this is B, then the intersection right here is A and B. So that's that. So mutually exclusive or disjoint is where there's no overlap. So mutually exclusive. Okay. So the addition rule, probability of A or B, is the probability of A plus the probability of B minus the probability of A and B. Why does that make sense? Let's go back to this. Well, if we had A, all of A, plus all of B, we just double counted this middle. So we have to take it out. We took all of A plus all of B. We just double counted this middle, so we take it out. So we get the addition rule. Other symbols are these unions for intersection. That's the same as or. And the N is the same as intersection. N is the same as N. Now, of course, for mutually exclusive sets, the probability of A and B, right, they can't have anything together that's equal to 0, so that goes out, and you can just add them up if they're mutually exclusive. But this is the general, this rule always works. If it's mutually exclusive, that will be 0, so it doesn't, so that will be 0, so it'll work anyway, so that's the general rule. Okay, so let's see it in action. So for an example, we have smoking and lung disease. So we have this set of data for percent of people of older men back a few years. So whether they're a smoker, not a smoker, has lung disease, does not have lung disease. And here are the numbers. So the number in lung disease is 15%, not lung disease is 85%. The number of smokers is 31%, and not smokers 69%. They both add up to 1, makes sense. So we can ask some basic probabilities. What's the probability that a randomly selected guy is a smoker? Well, you just add up these two, and you get 0.31, right? And what's the probability that he does not have lung disease? Not have lung disease, this one right here, you add up those two, and you get 85%. Okay, but now, let's do this. Has lung disease and is a smoker? Okay, so that's kind of the intersection of two sets. Intersection of two sets has lung disease, so this has lung disease and a smoker, so we're adding these guys. All right, it has to be both of those, so it's right just in the table. It's just this one, and that would be 0.12. But what about lung disease or a smoker? Well, lung disease or a smoker is lung disease plus a smoker minus the intersection, because we took lung disease, so we added this one, right? And then we did smoker and we added this one. We just double counted the middle one right here, right? So we can say it's just equal to, well, we take all the lung disease plus all the smokers, but we just double counted the middle, so we subtract that out, and if we add that all up, we get 0.34. Okay. The other way of doing that was that we could have just added this one plus this one plus this one, and we would have gotten that as well. Okay. So part 5, conditional probability, the big picture, is we take additional information can update our probabilities. Okay. And it's read probability of A given B. All right, so you have the probability of A given B. That means the probability of A given that we know B, or the probability of A given that we know B has happened. So conditional probability, adding some more information to it. Some ideas with that in the real world is the probability of amount of a claim given your driving record, years of driving experience, male, female, zip code, car safety features, etc. And of course, insurance companies use all this for these conditional probabilities. Sports example, a baseball manager changes his lineup depending on the opposing team, so it's a probability of win conditional on team being played and who's in the lineup. So he wants to optimize that. So conditional probabilities. Okay, computing the probability of A given B. Probability of A given B is just the probability of A and B divided by the probability of B, or the number in A and B divided by the number in B. And let's see that. Okay, now the probability of A given B, we know that B has happened, so now we're just in this reduced sample space. We're just in B. Now what's the probability of A given B? Well, it's just this part of B, this intersection here, and that is A and B. So it's just the probability of A and B divided by the probability of B, or the number in A and B divided by the number in B. Okay. So let's look at an example there. Following table lists joints probabilities associated. We have these, right? So now we can say, has lung disease given that he's a smoker? So what's that probability? Well, it's lung disease and a smoker divided by, well, probability of lung disease given a smoker. It's a probability of lung disease and a smoker divided by probability of smoker. And that lung disease and a smoker is this one, so it's 0.12 out of the total number of smokers. We're just in this reduced sample space, right? Just in the smokers, okay? We're just in the smokers here. So that's our reduced sample space. So lung disease, and you leave this as 100 people. There's 12 have lung disease out of 31. So it's just 0.12 over 0.31, or 12 over 31, which is about 39%. Okay. Now what about has lung disease given that he is not a smoker? Okay, now we're in the reduced sample space of not a smoker. So has lung disease, probability of lung disease given not a smoker is equal to probability of lung disease and not a smoker divided by the probability of not a smoker. Right now we're in the not a smoker space, so this right here, so that's 0.69. So lung disease is 0.03 divided by 0.69. Or you can look at it as 3 out of 69, right? And it's almost 4%. So probability of lung disease given a smoker is 39% versus 4%. What's the moral of that story? You got it. Don't smoke. Another lesson for that. Okay. Part 6, dependence and independence. Two events are independent if the occurrence of one event does not change the likelihood of the occurrence of the other event. The two events are independent. So the probability of A given B, the way we calculate it, probability of A given B, A doesn't care about B. It's just still the probability of A. Or vice versa, probability of B given A is just the probability of B. It didn't care about A at all. So i.e. A doesn't care if B happens. It's totally independent of B. Okay. We'll look at that in the next lecture. But so from that, we get the general multiplication rule. Probability of A given B is just the probability of A and B divided by the probability of B. And so if we just multiply up here, on that side, we get the general multiplication rule. The probability of A and B is the probability of B times the probability of A given B. And we could have listed A and B in the other direction, so we can interchange all the A's with B's. So probability of A times the probability of B given A. That's by mathematical symmetry. And you can view this as the probability of A occurs on the first event, then the probability of B occurs on the second event, given that A occurred on the first. All right. Now, general multiplication rule is used for finding the probability of A and B. Okay. And if the outcome of the first event somehow affects the probability of the second event, it's important to use that information. Okay. So, an assembler has been supplied 10 electronic components, for example, of which 3 are defective. If 2 are selected at random, what's the probability that neither component is defective? Okay. Well, that would be the probability of not defective on the first and not defective on the second, which by the multiplication rule is the probability of not defective on the first times the probability of not defective on the second, given that it wasn't defective on the first. Okay. So what's the probability of not defective on the first? Well, there's 10 components, 3 are defective, so 7 are not. So 7 out of 10, right? 7 out of 10 chance that it was not defective on the first one. Now, what's the probability that it's not defective on the second when we took one defective one out? So now one defective one is, or no, one non-defective one is taken out. So now we have 6 non-defectives out of 9 components, right? One chip was taken out as well. So the second one, not defective on the second, given not defective on the first, is 6 out of 9. So we multiply those across, and we get our answer, about 47%. Now, the multiplication rule for independent events. If A and B are independent, then the probability of B given A is just equal to the probability of B. So the multiplication rule, probability of A and B is equal to the probability of A times the probability of B given A. Well, that's independent, so that just goes to the probability of A times the probability of B. And that holds for multiplication, for independence. So for an example, say we flip 2 coins. What's the probability of getting 2 heads? Well, coin flips are independent. One coin flip doesn't depend on the other. So it's just multiplication, so probability of heads on 1 and heads on 2 is just the probability of heads on 1 times the probability of heads on 2. And that's equal to 1/2, right? Probability of heads on a coin flip is 1/2. 1/2 times a half, which is 4th, is a 0.25. And that makes sense, because doing it with sample space like we did before, our sample space is this. So it's probability of heads, it's 1 out of 4, and same probability. So that makes this multiplication rule seem plausible. Well, it in fact is certainly correct. Here's another example. Car accidents. Suppose that the chances of getting into a car accident is about 1 in 1,000, maybe about 1 in every 3 years. And they are independent. What's the probability that you and your teacher get into a car accident on the same day? Well, pretty low, right? It'd be the probability of A and the accident for one person and the accident for the other person. Since they're independent, you can just multiply those probabilities. 1 in 1,000 is 1/1000, so 0.001 times 0.001, and you just multiply them. The way you do that is you move this one over 1, 2, 3, so you have to move this one over 1, 2, 3, so an additional 3 zeros, and that's a pretty low probability. There's tens, hundreds, thousands, 10,000s, 100,000s, 1 in a million. Okay. And for the final example, suppose you have a couple of lights, you have 4 traffic lights on your way to work. The chances of them being red is, say, 40%, 30%, 30%, and 20%. what's the probability that you do not hit a red light on your way to work? And we won't worry about yellows. And we'll assume that the lights are independent. So you have red or green. Well, these are chances of being red, and we don't want not hitting a red, so all greens. What's the probability of greens? Well, we take the complement of this, that would be 60%, 70%, 70%, and 80%. Complement rule, right? So what's the probability of all greens? Well, you just multiply those together. Excuse me. 0.6 times 0.7 times 0.7 times 0.8, and you get about a 23-24% chance. So if that does happen, you got pretty lucky. But don't speed to make that happy, because if you'd be a ton more luckier if you did not get into an accident. So drive safely. That is a huge message. Okay, I hope this is helpful, and enjoy.